Okay, hello grade 12s. Today we're moving on to our next unit. We're just going to do a shorter lesson today on just the introduction. We're just going to do one page about Coulomb's law, which falls within our notes for fields. So we're going to be doing magnetic fields and electric fields. We'll start with electric fields and eventually move into magnetic fields. And then eventually we'll kind of talk about the forces of both of those and how they're related to one another. And that will bring us into our next unit after that, which will be electromagnetic induction. We might be talking about electric circuits first. I will let you know. So let's just jump right into it. I've attached to the Google Classroom post a PDF of your fields note booklet. So hopefully you can print it off. If you can't print it off, you can just follow along on loose leaf. It's the same thing. You can just do the practice problems with me. I'll be posting a solutions, all of the notes filled in for this booklet as well along with it. So if you want to work at your own pace, you can move ahead. I'll also be posting all of the solutions to the practice problems as well, all at the same time, like I did with the last lesson or the last unit, so that you don't have to constantly be reminding me to be posting them. So there'll be quite a bit of posts today. This lesson, like I said, should be actually pretty short. And then you can focus on just studying for your momentum work and energy assessment, which is coming up on Friday. So Coulomb's law is our first lesson for fields. It is about a French physicist by the name of Charles Coulomb. Charles Coulomb in French. He studied the forces between electric charges. He was around he was born in 1736, died in 1806. Just because we're doing distance learning does not mean that we will not look up a picture of him like we always do. Let's do that. Charles Coulomb. Here he is. Let's get a good picture of him. There we go. Open image in new tab, and I'll share that with you. You can probably imagine what he's going to look like. Why can't I do this? I'll do the entire screen. Here we go. And there he is. Hopefully you can see that. I think I did that right. There he is, Mr. Coulomb. So he spent a lot of his scientific life studying the forces between electric charges. And he came up with something called Coulomb's law, which we're going to talk about today. So Coulomb's law, what he found was that there was a relationship between how the forces changed, so the forces that both of the charges felt when the distance between the charges changed. So, and not only that, but also when the size of the charges changed. So a couple things. When he's changed the size of the charge, he found that if the size of the charge increased, so did the force it exerted on another charge. And if the size of the charge doubled, it doubled the electric force that the other charge felt. So there was a linear relationship, a direct relationship between the two of those. And he also found that when he changed the distance between the charges, so when we're looking at distance instead of size, we're looking at distance, he found that the force decreased when the distance between the charges increased. And the force decreased actually to the square of the distance between them. So it wasn't actually a direct relationship like this one. It was a square, an inverse square relationship. So if the distance was doubled, that meant that the electric force between the charges was only 1/4 of its original value. So it decreased by double of what the distance had changed by. Sorry, not double, by the square of what the distance had changed by. So his results can be stated as Coulomb's law, and the formula looks like this. The electric force, and this is equal to, the electric force is equal to K Q1 Q2 over R squared. Let's just take another second here to look at your formula sheets. Where do I have those? Right here. And you'll see right here, so what we're looking at today is we're going to be looking at this formula right here. This is Coulomb's law, Fe equals K Q1 Q2 over R squared. We're going to learn about what K is, and we'll still be using, this is review from grade 11 physics now, one elementary charge is equal to 1.6 times 10 to the negative 19 coulombs, or vice versa, 1 coulomb is equal to 6.25 times the 18 ECs. Okay, so maybe a quick refresher on that when you're doing the practice problems on your own today, or whenever you get a chance. We won't move on in this unit until probably Monday, because we'll be focusing on the assessment for momentum, work, and energy. Okay, so anyways, moving on. Let's get ourselves set up here again. Go. So, like I mentioned, we've got a couple new things to look at here today. The main new thing that we're looking at is K. What is K? And then we'll just mention what Q1 and Q2 are, what R is, and then what Fe is. So Fe is the electric force. K is something we call Coulomb's constant. Q1 and Q2 are the charges, and we measure our charges. We just have to be consistent, but we either measure them in coulombs or in ECs. Electric force is obviously, it's a force, it's measured in newtons. And then R is the distance between charges. Distance between charges. And we always measure distances in meters. So what does that mean about Coulomb's constant then? What is that telling us about Coulomb's constant? I'm going to put a little star here, and I'm going to write some important information about Coulomb's constant right down over here. There's a couple things that you see on your formula sheet that Coulomb's constant can be equal to. Coulomb's constant can be equal to, so K can be equal to 9 times 10 to the 9 Newton meters squared per coulombs squared. So that's if we're using coulombs, or if we're using EC, if we're using elementary charge, we get that K is equal to 2.3 times 10 to the negative 28 Newton meters squared per EC squared. So those are our two values that we can have for K, depending on what we're using for our Qs, for our charges in the problem. So if we decide to go with coulombs, we'll use this one. If we decide to go with ECs, we'll use this one. And then you'll notice there's two of them, so they'll nicely cancel. And then the meters will cancel with the meter squared on the bottom, and you'll end up with just newtons. So, reminder that 1 EC is the smallest unit of charge. So an electron would be negative 1 EC, or a proton is positive 1 EC. And then here's your little conversion factor for ECs to coulombs, in case you forgot. It is on your formula sheet though, so you can just double check it there. All right, and this relationship is directly the same, directly related to what this relationship is. Okay, so that's the relationship between those is very closely related to that, or it is directly related to that. That's where those two numbers come from. So anyways, let's do one example. I'm going to save the example on the second page, on the next page, for my next lesson, which we'll do on Monday, because it is quite the problem. It's a pretty challenging one. So right now, I'm just going to do this one, and that should let you do the first 4 or 5 questions. on Coulomb's law problems, and then we'll do the next half on Monday. So one model of the hydrogen atom assumes a stationary proton is orbited by an electron with a radius of 3 times 10 to the negative 10 meters. So basically, this is just saying like a Bohr diagram of a hydrogen atom, right? Has one proton orbited by one electron with a radius of 3 times 10 to the negative 10 meters. What is the electric force between the proton and the electron? I don't know about you, but before this, really would have considered what that would be, but there obviously is an electric force that's holding that electron in orbit. So that's what we're going to find right now. So let's just write out some of these things. Right here, this is my radius, right? That's my radius of orbit. So that's r, 3 times 10 to the negative 10. We're trying to find what Fe is equal to. And we can say a direction for Fe. We can. I don't always expect it, but in this case, I'm just getting my direction's going to be towards proton or towards each other, right? And how do I know that they're going to be towards each other? Well, because I've got an electron and a proton. These have different charges, right? We'll call this one Q1. It's equal to -1 EC. And this one is Q2, which is equal to +1 EC. So I guess that means that I'm using EC for my charge, which makes sense. I could use coulombs. I could use 1.6 times 10 to the negative 19, but I might as well just use 1. It's going to make my life easier. Now, one thing to consider is that these positives and negatives for the Qs are only there to show us whether it's an attraction or a repulsion. If they're the same, if they're both negative, it's going to repel each other. If they're both positive, they're going to repel each other. If they're opposite, they're going to attract each other. And what I mean by that is that we actually don't need to put positives and negatives inside of our Coulomb's law formula here. Okay, so what I'm going to say right here is for these two, I'm going to do a little arrow here. I actually just need the magnitudes. So what I mean is that I don't need you to put +1 and -1. It's just going to unnecessarily make your number negative. Just make sure that you're noticing right here. These are opposites. So just a little star here, opposites attract, right? Anyways, now it's time to plug in our values. Because I'm using EC, I'm going to use 2.3 times 10 to the negative 28 for my K value. So 2.3 times 10 to the negative 28. And then it becomes kind of silly here. Q1 is just 1, and Q2 is just 1. Now Q1 is technically -1, but like we said, we're just using the magnitude. We're just using the positive values. And then dividing by our distance between them squared. So 3 times 10, 3.0 times 10 to the negative 10 squared. And there you have it. If you plug all of that in your calculator, you should get something that looks like 2.6 times 10 to the negative 9 newtons. And for my direction, I'm just going to say towards each other. There we go. All right, so that is it for our little introduction to Coulomb's law. If you have any questions, just let me know. And if not, you can work on, I think for these problems, you should be able to, with what we went over today, you should be able to at least do 1 to 5. And I think you could even do 6. 7 and 8 is a little bit trickier, especially 8. I even have a note here. You can try this, but it's difficult. Those will be trickier, and you're probably going to want to wait until we do the next lesson together. that next example on the back side of the page here, right here. It's a tricky one. So anyways, we'll end it there. Good luck studying for the momentum, work, and energy assessment that you're going to have on Friday. You'll have a few days to do that. Please, please, please let me know if you have any questions. I am more than willing to help you out. So you can just email me, okay? Have a great day. We will talk to you later.